Okay, so now the next couple slides and talk will be about numerics and actually how things are integrated. And we'll start to get into how WaveWatch works on this aspect. So I have two versions of the more or less the same thing. And so one thing which is very funny for the users of WaveWatch is that you have to find 4 different time steps. And the reason for that is that the wave action equation is integrated with the splitting method. So for people that are familiar with ocean circulation models, it's a bit like the baroclean barotropic splitting. So you have some terms are in the baroclinic equation, some terms are depth integrated. So here in our case, we have the advection terms on the left-hand side and the source terms on the right-hand side. And the time scales of evolution of these different terms can be very different. And the idea is to integrate these terms as efficiently as possible. And so for some terms that require very fast dynamics, you want to have a small time step. For some other terms, you want to have a different time step. And this is what is done in WaveWatch. And so the 4 time steps, so there's one, the first one is the global, what's called the overall time step, which is the time of integration of the full equation. And then during this overall time step, we're going to do some fractional steps for different pieces of the equation. So the second step is for the advection in space. It's fun, yeah, written funny here, but it's just the advection in space. And that time step is constrained by stability criteria. And so here, it's a bit a function of which numerical scheme you're going to use in WaveWatch and which type of grid you're going to use. So you have the options at the with the name list parameters to choose either some regular grid or some triangle-based grid. On the regular grids, we only have explicit numerical schemes, which means that they are stable if the integration over one time step is not jumping over one spatial cell. That's the CFL condition. So if you're jumping too fast in one time step, the thing will just become unstable and could blow up. On the triangle meshes, you have the option of using either implicit schemes or explicit schemes. And I'll talk later about the benefits of one or the other. Yeah, so if you're using triangle grids, the time step will actually be adjusted to your grid, even if it's explicit schemes. If it's a square or regular or curvilinear grid, you have to choose the time step. So you have to make the decision and compute what is a stable time steps. And there actually, you'll see this afternoon in a tutorial what happens if you make a time step too big. It just gives you some garbage. So that's the second time step, the advection time step. Then you have the another advection time step, but in spectral space, because as we discussed, the waves turn around, and we have a discrete spectrum. So we have different directions. We need to move the energy from one direction to another direction, and so this turning is actually an advection in direction space. And there is a different time step possibly for that. And then finally, there's a time step for the torso integration, the right-hand side. And in practice, this is done with an adaptive time step. And in order to make sure that it doesn't take forever, there is a minimum time step you have to define. Basically, the integration will look at the changes of the spectrum. If it's changing too fast, it will reduce the time step until it reaches this minimum value, and then say, okay. In that case, I will apply what is called a limiter. It means that instead of actually solving the equation you try to solve, it's just say, okay, I'm not going to change the spectrum so much because otherwise it can give some bad results. So there is a limiter in the source term integration. If you have time steps small enough, and usually we use between 1 and 10 seconds, the limiter is almost never used. So at least you're doing something clean. So these 4 time steps, they are in that order in the input file for WaveWatch, and I will show you the logic of the input files after that. And we will discuss the TFL condition, because this is what will make the model stable or not, and so you want to give the right values for that. And in practice, you will find examples, especially in the reg test. There is a regression test folder that comes with the WaveWatch package. You will see that this afternoon, and you will see you have many different test cases if you want to play. So the TFL time step, yeah, it's only for the explicit finite difference propagation schemes. And as I said, it's there to make sure that you don't jump over one grid cell or one time step. It's a bit dependent on the propagation scheme. So the first order or the third order are slightly different stability conditions. And also, there is something which is special to spectral wave models, is that because they have a discrete grid in spectral space, you have a discrete spectrum, so that your energy is traveling at discrete speeds and discrete directions. And so if you have a uniform storm, it will travel as a flower pattern, with waves going in each of the individual direction. And of course, in reality, it should be smooth. So to reduce this, what is called the garden sprinkler effect, imagine something which is watering your garden, which is turning and sending water, that's called garden sprinkler, like for putting water on the lawn. To smooth that effect, there is a special smoothing operator, and that smoothing operator introduces some stability issues in numerical schemes. So the stability of the scheme is not just due to the actual advection scheme by itself, but also to the choice of the smoothing operator, which is used to mitigate the garden sprinkler effect. Right, and yeah, so if you make the time step too big, it will blow up. In practice, in the code, this time step is adjusted as a function of the frequency, because it's short waves that travel slower. So you can use a bigger time step for the slow waves because their speed is slower. Okay, and that is done automatically in the code. And the same is true when the current changes. Which means that in practice, the time step of integration will change with the current, and so if the model becomes slower, that's maybe the reason why. All right, so the overall time step is this first big value which is used to integrate the full equation. It's like the rendezvous time steps for the entire equations, because we're integrating the different bits. And typically, you don't want to make the global time step not too much bigger than the refraction and advection time steps, because what may happen otherwise is that you may advect stuff in many, many steps, and then you compute the source terms after having doing the advection, and maybe you're going to miss the action of what was happening before the wave was propagating. And so what Henrik is advising is maybe a ratio of a factor of 2 to 3 between the global time step and the advection time step. Yeah, we'll show that. And then the third time step, which is due to the changing of the wave in direction, or where you also have varying currents, is due to the changing of the relative frequencies of the waves as they go into different currents. There's something special which is done with this refraction term, is that if the velocity of refraction becomes too large, if it's very large because you have a steep slope or you have a very strong current shear, then normally the wave should turn a lot. And if they turn more than one spectral bin, like say 15 or 10 degrees in one time step, instead of blowing up, what's done in WaveWatch is that the refraction will be limited. So instead of actually computing the full turning of the wave, WaveWatch will only compute part of the turning of the wave. Right, so you have to know that, and so the results of the model can be different. Of course, if you make a big refraction step or a small refraction step, because you're not going to actually integrate the same equation. And this filtering, this refraction actually involves the turning due to the depth slope, to the shear of the current, because waves turn when you have a shear. But also when you're working on the globe, the apparent direction, which is reference relative to the North Pole, if you're going to high latitude, the waves, they go straight on the globe, right? So it's a great circle path. So actually, if the waves go straight to the north, if you go through the North Pole, if you have no ice, the direction will flip 180 degrees. So you have a big jump in direction. If you just go very close to the pole, it's not going to jump, it's going to change very fast in direction. And that is also a problem with the numerics of the code. So this turning term also includes the apparent direction effect when you go to high latitudes. And actually, if you have a single grid, for example, of North Pacific, your time step are going to be driven partly by what's happening in the north of the Gulf of Alaska, because you want to get these waves properly. So you have to be a bit careful when you go to high latitudes. And this is a reason why, this is one of the reasons why the model has usually been limited to something like 75° north or 80° north. The problem that it used to be only sea ice in the Arctic, and so we didn't care about it. Now we actually have sea ice edge, which is going beyond 80° north, and we have actually ice that can travel through the Arctic, and we actually have some projects to work on this. So we're now modifying this to shift the North Pole somewhere else, like people have done for the ocean. People are doing some different grids, curvilinear. Actually, these days we're running with a curvilinear grid porostrographic on the Arctic, but we still have this issue of the advection scheme for the direction. So you need to find some other reference. And version 5.08 doesn't still have that, but I'm sure that version 5 point something from next year, which should be the official release, should have the stick for having a different reference, not at the North Pole, but maybe somewhere in Siberia, so that the waves don't jump 180 degrees when they go through the pole. All right, so that was the there is this refraction time step you have to be aware of, and the problem that here it's not going to blow up, it will just complete, but it will not tell you that it will use a smaller refraction. So I strongly advise you to run your model with different time steps and make sure that it converges as a time step goes to small values. And yep. So the way this was done, yeah, and now the last one of the 4 time steps, the source term time step. So the way it was done in the 1980s, and the way it is still done today at STMWF, is that the source term is integrated with just one big time step. Now, if you look at the waves at the sea, you will see that the short waves, it change very fast. Long waves, it change slower. And if you want to resolve what's happening with the short part of the spectrum, you typically have to use a time step of maybe 30 seconds, depends if the wind is changing very fast or not. And so what was done in WAM is we have this one big time step, the model is trying to change very fast, and in order to avoid spurious oscillation and stuff like that, what's done in WAM is that okay, just put the limiter. Okay, if the change is too big compared to a reference change, we just say that the source term is too big, we don't change the spectrum so much. This is still used today at STMWF. They have a 600-second time step, 10 minutes. Okay. In WaveWatch, there is an adaptive time step, and so if the total source term is very big, then the time step will be reduced to make this change relatively small, so that it's actually well resolved in time. But of course, there is a safety valve because you don't want to run to go forever, so there's a minimum time step for that. And this has a big impact on the solution. And so these slides are from Hendrik Tolman. So he was the one to put that in the face of the WAM group. Hendrik was part of the WAM group initially, but he hated this limiter so much that this is why he created his own model, essentially. And he had a hard time to publish that because the WAM community was just really up against him. And so it was finally published in 2002 in a Global Atmosphere Ocean Systems paper. And yeah, so the impact of limiter is really big. And the reason why Météo France only changed to WAM 4 years ago is that the limiter in WAM has a big impact on the solution in the Mediterranean. So at short fetch, they had undergrowth, so the wave were growing too slow, and the old second generation model was still much better than WAM even 8 years ago. So that's examples. All right, so you take a homogeneous ocean, you blow 40 meter per second winds. You start from rest. And so you see that if you use a 20-minute time step, you get this growth curve. This is 10 hours, 1 day. If you use a very small time step, you converge to the green curve. Okay, so it means that after 10 hours, difference between 3 meter wave height and 6.5 meter wave height, right? And today, CMWF are using 10-minute time step, which is this pink curve, and it's still a difference of 1.5 meters. And you know, as I told you, we're chasing biases of a few %, so this is just crazy. But well, you know, and if you reduce from 10 minutes, then 5 minutes, and then 2 minutes, and you slowly converge to the solution. All right, so that's just the old limiter, the way it was used. So in the meantime, people have done some slightly different things. So they've tried to use different ways of defining the limiter, and so you can get these kind of different curves. You go from something with converging, but then actually it can overshoot for some different time steps. So there's different solutions to the limiter problem. And so that's the issue also with the frequency. We can have the shape of the spectrum can be very different if you have different time steps. So this is yeah, one example of the integrated Thorstrom integrated spectrum, and the solution actually should be this green one. So these limiters can have some impact on the solution, and so you have to know about that. And so this is the reason for having this adaptive time step, to make sure that you actually converge to what should be the proper integration and the proper balance of the source terms. All right. So the next slides are about the way that waveWAT can be run with not just a single grid, but now with multiple grids. And the idea of doing this multiple grids is that in some places of your region, you want to resolve better the waves. Maybe you want to use a different time step, and you want to adapt the time step locally. And this is what you could do with nested grid. So one simple way to do that might be to do some domain decomposition and have the same resolution everywhere and do something like that. What Henrik introduced actually to be able to have different resolutions on the different grids. And so you can actually do this kind of thing here. This is an example of a current ring and or eddy, or yeah, and that's the current field. And what is shown after that is the way it is done with 3 grids. We have one grid here, which is cut like that with high resolution, and then you have another grid around it, and these 2 grids will communicate 2 ways. And the way it's done is that you have this one grid with a big time step, and you can have some finer grid with a smaller time step. And so it's going to communicate from the coarse time step to the finer time step, integrate the fine one, and then go back by averaging and move back the energy to the coarser time step. So in one instance, you provide boundary data to the fine model, and then when the fine model is finished, you average on the coarser grid to get the information for the coarse model, and then you advance in time again. And there was supposed to be an animation of that, but I guess Mikael transformed that in PDF, so we don't see anything anymore. That's all right. You get the idea, right? And of course, you don't have the animation, and that's the final result. In this white case, you have a hurricane, and there's really 3 different grids, and you actually don't see the edges of the grid too much, and so that's the a multi-grid mosaic of the result. And yes, that's all I had about the time step issues. And yeah. So you have these 4 different time steps, and in the multi-grid case, each model has its own 4 different time steps, and the rendezvous of the grid happens at the global time step. So you will integrate the coarse grid, and then you integrate the small grid to get same time level. Then you do the averaging, and it goes forward. That's strange. T'as une question? Ça te paraît bizarre? Mm-hmm. Okay. Okay. Well, I guess one of the easy things with Waze is that we know where they are going. So it's like a heuristic method. So it's less prone to instabilities as ocean circulation models. But so yeah, this is the way it's done. So this is an example in which you have three ranks of grids, so the coarse grid, a medium grid, and a fine grid. In that case, there's a factor 3 between the three global time steps. So what happens is that this is run first. After that, you run this one. Then you run one step, and you average. Then you run this one, then top, and then go back here, do that one, and top, and then you average, and then you do that one. Yeah. And I would have to check what happened at the boundary if it's interpolated in time. I think it is, and so I think that's the reason. I think the boundary condition that's provided by the big guy is interpolated in time between that time and this time. To make it, I'm not sure about that. No, there was one case. There's a version of there's a switch to have a moving grid, but it doesn't support. It's only good for bathymetry, flat bathymetry without shoreline. The issue then is to have the depth change and the shoreline move. It was for hurricane studies in the US, and I don't think they've changed that to be able to support bathymetry and shoreline. But if you want to know more about that, you should contact Enrique Alves, because he's the one that developed this moving grid for being able to resolve what's happening in a hurricane at high resolution by following the hurricane. All right, so the next short one, still about numerics. So yeah, there's only other question about time steps. Yep. Yes, and also